This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good afternoon, everyone. I think we can start. So a lot of people in the room, so we should be mindful of the neighbors, be quiet, right? Okay. Yeah, it's easier when the room number of people are smaller than less noise. Maybe a couple of things to announce. I keep posting the solutions, handwritten and typed, and related to that, I sent an announcement. In question 7 turned out to be more tricky than I initially thought, and then even worse, its solution that I had was wrong. So it was a subtle mistake I haven't realized. So, but what I posted with the remark is correct. So you can have a look. It's a special case where you have the best. If you do line search, optimal step size turns out to be constant throughout the multiple steps. That's a very, very special situation that doesn't happen in other general normal problems. So that's that. I hope the workshops are going okay. Some of my demonstrators said it takes a while, but that's maybe normal. It's the first main workshop that you're doing. And the submission deadline will be 1 week after you finish it. So there will be additional time for you to finish. And then everyone has the things in your devices, right? And that's I find them the most meaningful and fun parts of the subject. This lecturing thing is okay, but it's very old school. Even problem solving is better, but yeah, still that's old school too. This is something you do. Optimization and especially machine learning is something you do. You don't, unless you're a mathematician, then you write theorems. That's a different thing. But as an engineer, it's something you do, and then you're doing a version of it, a simple version of it, in the workshops. So focus on those. Anything else? Anything that I forget? Yep.
Sorry, could you clarify the due date for the workshop?
Yeah, I'll post it today. Yeah, the 1 week after the last session. So this is a 2-week workshop. So the workshop will end, that week will end, and you will have 1 more week. And I might give additional weekend or something, because we will not have workshops during the mid-semester test. So that gives us another week. Maybe first 2 workshops, we can give extra time, and by that time you will be all Python wizards, and the 3rd, 4th you will do it maybe more smoothly. Yeah, I'll try to give as much time as possible. I need to be also mindful of not overlapping them too much. I don't want people to work on the first one to miss the second one and so on. Yeah, it's a bit. But we have teaching break too, so probably we'll be safe. We'll be safe. Yeah. Does that answer? Yep. All right. Thanks for that. Very good. So let's continue. We have been talking about deep things when I finished the lecture last time. Convergence of iterative algorithms, and as you have noticed, whether you do some type of a gradient descent, a gradient search, or cutting plane methods, they're all iterative algorithms that solve the optimization problem, right? So then the question is, when will these algorithms work? We are not happy as engineers if they work from time to time, especially for mission critical systems, right? So the more we can say about these things theoretically, the better. It's not always possible. Systems can get complicated, but the more we can say, the better. And then I mentioned what does it mean to converge of a sequence. You see all that calculus that you forgot was useful. Try to re-remember it. And then we talked about convergence analysis. There are 2 big main approaches that I know of. One of them is this descent function or Lyapunov function or energy function approach. The main idea is extremely simple, and I only want you to have the concept. If you do advanced control, you need to learn Lyapunov functions anyway. It's at the center of nonlinear control. But there the idea is simple too. The idea is if you have a solution, hopefully we have a solution in our optimization problems, around the solution or solution set, if you have a flat bottom of a ball, for example, you put an energy function, any type of shaped ball around that solution where the solution is the bottom, right? And you have infinitely many options for that. You can shape it as you like, and then you shape it in a way to match your algorithm so that you show that your algorithm climbs down in that shape. And then if it climbs down, if it hits the bottom, if it's the bottom, you have proven that it converges. That's it, right? So the main idea is very, very simple, very, very intuitive. There's some nice math. Actually, the math is also simple. The next step should be, lower than the first step. We are talking about minimization, of course, here. When you are maximizing, you can reverse the sign. And you can use the objective function itself, but as I said, you don't have to. You have like infinitely many choices. As long as your energy function goes, to a solution, hits the zero there, then you're fine. Another option is norm of the gradient, because we know that gradient goes to zero. Norm of the gradient will go automatically to zero as well. That's another immediate choice for a descent function, right? If you want to prove it or argue about it. Okay, the other big approach and class of ways to show it is show that your algorithm is a contraction. So then I gave you the definition of the contraction mapping. That means, you take any 2 points in the space, then after you implement your algorithm, the step t of x, right, which is either the cutting plane or the gradient step, right, xn minus alpha d, right, d being whatever, then your next ones should be closer to each other than the previous step. That kind of also is intuitive. If they become closer and closer, alpha is less than 1 here, between 0 and 1. That means you are really contracting. This is a good name. And then it's supposed to go to a single point, no matter which 2 points you started with. And that's called the fixed point of the mapping. So at that point, when you iterate once more at the solution, you're supposed to stay in the solution, not jump out. That's the case for all these gradient algorithms. When the gradient is 0, then the right-hand side becomes 0. Xn plus 1 becomes xn, right? Because the derivative d becomes 0 there. And then actually that intuition is indeed the case. So we have this proposition that says, it contracts. It not only says that, but there exists a unique fixed point. And if we have a contraction mapping, if your iteration is a contraction mapping, and it converges geometrically, sometimes this is also called linear convergence because of this linear factor. So as you go on, the alpha to the t means as t goes to infinity, alpha is less than 1. You asymptotically goes to 0, so that means your distance to the solution becomes 0, and then that means another way of saying I have converged to the solution of my optimization problem. Right? Notice that these definitions are general. These are valid for any iterative algorithms. Applying them to optimization algorithms is a special case. So what you're learning is even more general than optimization, actually. So it's useful knowledge to know this stuff. So here's an example. This is the fixed point of this mapping. If you see this mapping here, we can use our pen. Right? So in one dimension, if this is your t of x, then this is your fixed point, because at that point the answer stays the same. It intersects the diagonal. And if you start from here, you just look at the mapping, then that gives you the next point to look at. You do that, next point to look at, you do that, and hopefully if it converges, it goes closer and closer to your fixed point. Then it's a contraction if that happens from any starting point, right? So this is a fancy way of showing it, like a staircase type of thing. So the question that I said this will not be in the exam, this is a bit advanced, but I only included it to show how this thing works in a more formal way, is this question. I'm going to do it and then continue with a couple of minor things and start the constrained optimization. So prove that this is this is correct, and then I gave hints to myself and you, and this is specifically we need to show the iteration results in a Cauchy sequence. But if it's a Cauchy sequence, then we know that it converges. So that's another way of saying show that it converges. it kind of gives you a hint there. And then X is unique. There cannot be two different solutions if it's a contraction mapping. And then also show the geometric convergence using an iterative argument. I have also given the what a Cauchy sequence means. So let's do this together, as I said, to get some type of intuition, more practical understanding of that through the example. So we have this. So let me get my black. Okay, is it too small? Hopefully not. Maybe a bit more. Yep. All right, it worked. Good. So first we should start with the Cauchy sequence. Can we show that this is a Cauchy sequence? So that's it turns out we can do that. First we write what is a contraction mapping so that we have it in mind. So from any 2 points, this is the mapping applied to these points. So that should be less than or equal to some alpha x minus y. These are all vectors, and T is a mapping. We have then we have also alpha is between 0 and 1. Alpha is less than 1, otherwise it will not contract, right? It may stay the same. So that's why it should be written like this. So if we write it, based on this, we can actually write it xn plus 1 equals t of xn, right? Let me write it with the t's, t plus 1 and x of t. So, because we were using t as the step size, t equals 0 to 1, to goes on. So we can actually write x as x of t on the right-hand side, and we can choose y as xt minus 1. We can choose any point, so this is legitimate. And when we apply the t of x, on this side we will end up with x of t plus 1 here, minus x of t here. All right? With some norm. Whenever you see norm, you can think of Euclidean norm with the square. That's a special case, but that works. So we have this for all t. What does this imply? If I apply this for all t equals 0, 1, that, and then this implies that if I apply them one by one, I immediately get this result. So that if I start with t equals 1, then it would be x1 minus x0, and then we will get x2 minus x1, and then I apply again and again and again iteratively. So I end up with, let me use my cheat sheet here a bit. So I end up with x of t plus 1 minus x of t. I can write this in terms of the x1 minus x0, which are the initial points that I've chosen, iterated over. As you can see, this is not an unexpected result. So now I need to bring it to the Cauchy form, and that's all I need to do this is show that it's a Cauchy sequence. Then once I do that, because of the if one and only if it's a Cauchy, then it converges, end of the story. Mathematically, that ends the story. So actually, then I need to do this difference between them for something greater than a number k. So one way to write this down, so let me write it this way. So I can do this x of t plus m minus some x of t, and then I can write this as, x of t plus m minus x of t plus m minus 1 plus x of t plus m minus 1. You can do a lot of pluses and minuses in between that will cancel each other, right? You can do that, add, subtract, nothing changes. So this will be then equality, actually. And this is equal to that. Then you can use the triangle inequality to give each of them a separate one. So then I will have a sum of I equals 1 to m. I will have x of then t plus I minus x of t plus I minus 1. Right? So then I apply the triangle equality multiple times with the norm. And then the rest is this. We know the formula for these, so I kind of use this one for this. So star then U star here for each of them. And once I do that, because it goes until t, at t I have the alpha to the t. Now I'm going beyond t, alpha t plus 1, alpha t plus 2, and so on. So we end up with, once I apply this alpha to the t, all of them have that. But then after the first one, there's one more alpha, square, dot, 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 alpha to the m minus 1. Each of them can be written in terms of x1 minus x0. Okay. And then using the series, because this is a partial sum, if and alphas are all positive, if you add additional terms, you cannot go lower. So we can actually make it in a lazily infinite series out of it. And then infinite series of that will be 1 over 1 minus alpha. This is less than equal to infinite, 1 to infinite of alpha to the k. Actually, shall say 0. So this term will be less than that. Therefore, this is equal to that. And times, again, x1 minus x0. Right? Maybe this is very messy. Sorry about that. Let me write it this way. So this is equal to, this is a side note with the green. This is equal to k equals 0 to infinity alpha to the k, which is greater than equal to k equals 0 to m alpha to the k, right? So therefore, this is bigger than that. I can put it to the right-hand side of the inequality. Notice the inequality is here. And what does that mean? So that means if I choose a t big enough, for a big enough t, for t large enough, there exists an epsilon such that, you know, x of t plus m, sorry, this is the other way, x of t plus m minus x of t is less than epsilon, and the epsilon will come from the right-hand side, right? This is fixed, t, you make t large enough, this is also fixed, that will get smaller and smaller. But that means it's a Cauchy sequence, hence this xt is, let's write it the proper way, x of t is a Cauchy sequence. And then it's the, once you have that, you go to proposition A5, therefore it converges. Here we are. We have shown that it converges in a, you know, doing some nice elementary mathematics. Elementary for mathematics majors, you know, may not be that elementary for us, but and then the next thing to show is we need to show that it is a fixed point. It converges, but we don't know what it converges to. So we need to show it converges to an x star, and the next step is that, right? So we need to show that it converges to an x star. So we haven't shown that it converges. It's a Cauchy sequence. It converges, but what is the second part, the x star? So we can write it in this way: t of x star minus x star, right, will be then, we can write this again with using a similar trick as t of x star minus xt plus xt minus x star. And that is, again, using triangle inequality. We get that t of x star minus x of t plus x of t minus x star, right? But then we can write this this one in terms of right-hand side as alpha x star minus x t minus 1. So t of x star, then we need to show that t of x star is x star, right? So this is less than or equal to x star minus tx1 minus 1, and then plus x of t minus x star. That's the other term, right? Since we have shown that x of t converges to x star, right? So we get then we get the right-hand side goes to 0. And because right-hand side goes to 0, t of x star goes to 0. Therefore, t of x star equals x star, which is the fixed point of t. Here you go. So, but is this the only fixed point? Then you need to show again. It's a nice, step by step. You need to. It's all about clear logical thinking. The next step is, then I need to show it's a unique fixed point. Then you show it by contradiction. Show by contradiction that it is unique. Right? How do we show that by contradiction it is unique? Let's say there are two different ones, x star and y star. Assume they are different. Then, because we have this, tx star is x star, we can actually write it as t of x star minus t of y star is the same as x star minus y star because of the previous result we have obtained. Right? But this is less than or equal to alpha times x star minus y star, which is from the basic definition. Right? But then alpha is less than 1. So you cannot have something, the only case a less than or equal to alpha b for a b greater than 0, greater than or equal to 0. The only way to satisfy this a equals b, right? Otherwise, it doesn't work. So, but a equals b means they are equal. So we have assumed they are different, and then they are equal. So it's a contradiction. So they have to be the same. Assume there are different ones, and then we have shown that they cannot be different. Indeed. So there a equals b means x star equals y star. All right. So I'm not saying this is the most perfect mathematical proof, but it's an illustration of how these things are proven, right? And yeah, I'm not. This subject is not about proving things, so this is not something I expect you to do in the final exam. But I can expect you to have a clear thinking capability of, understanding the concepts. Maybe that's asking a lot, but yeah, still. Hopefully, it will be yeah. A and B, yeah. A and B equals to 0, right? That's what I'm trying to say. So I was trying to say insides, right? So sorry about that. Excellent. Thanks a lot for that. A equals B equals 0. Therefore, this was A, this was B, right? So that means they are equal. Thank you. I did it on purpose. So yeah, catch it, yeah, please. All right. So that's the one way of if you open Bartsekas's books, one of them is freely available online, the other one is not. Yeah, it's full of proofs like these, and once you understand what's going on, actually they are really nice. Actually, a good mathematical proof should be easy to understand. If it's too convoluted, it can be an advanced topic, yes, but the clean math is supposed to be clean and step by step to understand. Shouldn't be mysterious. All right, so we also shown that it is going with this geometric convergence, right? So that is this. I have shown this on the way while proving the thing. So that's I have also shown. So that means at each step I make a big, reduction by alpha in terms of distance to the solution. It's not always possible to show contraction. Therefore, there is also this thing that's called pseudo-contraction that you should maybe know about. In this case, it's a weaker result. So you are now looking at it with respect to the solution x star. So you assume there is a solution here. Suppose that there is a fixed point. And then you are looking at each iteration, does it bring me closer to the solution? It's also very intuitive. At each iteration, I'm coming closer to the solution. Initially, I'm here. After the iteration, my distance to the solution is less than this distance to the initial. Here you go. That's what it means. That's called as pseudo-contracting, and it also satisfies this, but it's a weaker result. There is a proof of it. I'm not going to go over it, and it's just another way of dealing with these if you want to show whether your algorithm converges or not. Convergence doesn't always need to be to a global solution. Sometimes you do these contractions and descent convergence results only for local solutions, in a neighborhood of a local minimum. You can actually construct it. Then the construction is not from any starting point, but only from starting point in the neighborhood of that solution. Then you show that locally I'm converging. This is especially important when you have a very hilly landscape, as we discussed, and then there is no nice convexity or quasi-convexity of your objective function. Any questions or other good comments? All right. So let's. I would like to conclude the discussion with the defects of these methods. I mentioned that cutting plane methods, the big headache there is if the dimension of your problem, meaning the dimension of your x vector, number of variables in your optimization problem, they're all the same thing. They go large, like if you have 100 variables or dimension of your x is 100, then the space you need to cut is 100 dimensional. That's a very cumbersome thing. So those methods are not dimension-free methods. Sometimes people call them not dimension-free methods. Gradient method doesn't have that. Gradient method is dimension-free. You just jump, no matter how many dimensional your step is, and go to closer to your solution. But that method is also not, especially steepest descent. Both Newton methods and steepest descent, they are not perfect, and they can actually behave very, very strangely for certain cases. So to illustrate that, let's look at this quadratic optimization problem. We can illustrate it with a simple one without complicating matters. So this is like a parabola, right? Multi-dimensional parabola, like ball-shaped, or hyperbole, if there is such a word. Then if the Q is positive definite, then this is convex, right? It's really ball-shaped. If it's negative definite, it's like a mountain in n dimensions. And we know that the solution satisfies this when we take the derivative and apply the chain rule. We know the solution is this, but let's look at the steepest descent algorithm that will have this form that xk plus 1, k being here the iteration steps starting from k equals 0, xk minus alpha k, that's your step size, which may or may not be coming from line search. And then this g is the derivative, right? And derivative of this is then, because of this nice 1/2 here, comes to the qxk minus b. So once you write it down, okay, there's nothing here. One-dimensional version, you should be able to write this even in high school. But this is the multivariate version. It looks a bit fancier. Q is a matrix, x is a vector, b is a vector. Now, let's look at this thing that we did in question 7. We can actually find the optimum step size. And maybe this is even a better example, because the step size calculation is much more clear and clean compared to that specific question. So you write then the f of xk minus alpha gk. That is actually f of xk plus 1, right? And then what will give me the best f of xk plus 1? I have chosen my direction. I am doing steepest descent. I'm looking at the gradient, first order. I need to write this down and then minimize this with respect to alpha, right? I need to choose the best step size. It turns out here it is actually less headache. If you do a little bit of effort and be careful about the multivariate derivatives, where the matrices end up and whether they were transposed or not, you end up with this, actually. So your alpha is a function of your q, but also at the alpha k is the function of your derivatives. right? Gradients, not the derivatives, gradients. So you see it is different in each step, unlike that question 7. As expected, my line search should give intuitively, most of the cases, it gives a different result because it's supposed to get also smaller when I come closer to the solution. Is that the case? Yes. As I come closer to the solution, the top one is the dot product, or norm actually, of the gradient. As I come closer, the norm of the gradient will go smaller and smaller. My step size will get smaller and smaller too. So it intuitively makes sense. You can do a sanity check like this, whether you can check these things like whether you have made a simple mistake or not, typo or not. Anyway, so once we put it in, so this is my steepest descent, right? There is, after many more steps actually, which I decided to skip, I want to say something that come to the point of the result. So we have this, if we have a function which has the Hessian, and just like that, in this case, the Hessian is Q, positive definite matrix. And then we look at the Hessian, and then its smallest eigenvalue and largest eigenvalue. You see that plays a role in the step size as well, and in my gradient. And then what does it say? Let's read this. Suppose we have an f defined on R to the n, has continuous second partial derivatives, and is a minimum x star. An example is the quadratic one of that, but this is more general. Suppose that Hessian matrix, now you see this book calls it F. We were calling it H. I like H more. Has the smallest eigenvalue A and largest eigenvalue capital A. If xk is the sequence generated in the method of steepest descent that converges to x star, like we have the example here, that would be this guy as an example. Then the sequence of objective values, of course, for each x, there is an f of x, so that's another parallel sequence that you're automatically generating, converges to x star linearly with a ratio of no larger than this. So this, and then if I define an R, ratio of the largest to smallest eigenvalue of the Hessian matrix, capital A to small a, I can take this ratio and write it in terms of these R's, right? This ratio, small r, the ratio of the largest eigenvalue to the smallest eigenvalue of your Hessian is called the condition number. Now, what this shows is if your f of xk converges to fx star, and with a convergence ratio of this, what do you observe here? So if your R is very large, you know what happens to this factor? This factor goes to 1, right? So what does it mean? This ratio, convergence ratio, is how much you converge at each step. If it goes to closer to 1, actually that means I'm not making big progress, right? And that's exactly what's illustrated here. So if I start from 0, you see this is a kind of a pathetic case. So I start from 0, 1, 2, suddenly this is starting to jiggle, and then, you know, it takes forever, thousands of steps to converge. There are many cases like these. The way to locally analyze if I'm stuck or not is actually, you can locally find the approximation Hessian, just like we were doing in the Newton method. And if the condition number is large, then you're in trouble. If it's just a quadratic optimization, condition number is large, you're again in trouble. If condition number is small, it's okay, right? Then you will be converging fast. So this is also called ill-conditioned. If condition number is large, we talk about ill-conditioned problem, and then the convergence will be slow. Convergence will be slow. Because this convergence factor that relates the next step value to the previous step value will be closer to 1. That means I'm not decreasing my f enough with my steps. So that's why it takes forever. We ideally want to steeply decrease it to find the bottom of it. And actually, I don't have to talk too much about this because you're going to do it in the workshop. Right? Remember, you solved that question? Not everyone has the workshops yet, right? No, no, good news is you have it in the workshop with the quadratic optimization problem, and then you will have a Q and then different Q where you have this ratio of the largest to smallest eigenvalue being, different, and that will give a chance to see it with your own eyes, like, oh, it takes much longer if it's worse conditions compared to the better conditioned problem. Right? That's good because I don't have to draw too many things to convince you. So you'll experience yourself. The derivation of this theorem is a bit long. Should I have included it? I mean, mathematically I should have, but then, as I was saying, we will then spend like 1 hour to derive that theorem. So I decided not to include it unless there's an overwhelming desire to include it, if I'm inundated with my emails. But you are not bound by what I'm doing here. So this is from Lundberger's book, and it is just in the reading suggestion. You can go and read it and see the derivation yourself. So there's nothing mysterious there. I just copied this theorem from Lundberger. Maybe I should have said which section. I will do that in updating the slides. All right. I also tried to do this to give you guidance on what you should know, because I keep saying you should know the basics, but it's a very legitimate question. What is basics? So I'm trying to answer it here, which is very much matching with what I am covering, but maybe it's a kind of a hint for what to expect in the exams and so on. All right, so I'll continue trying to do that. And that concludes the unconstrained optimization part. Now let's go to constrained optimization. Actually, the reason why you start with unconstrained is very simple. You can introduce all these concepts without worrying about the constraints. And then in the constraint versions, the transition to constraint versions is not a big intellectual jump. So if once you understand the main idea, constraint version just is a twist in some aspects. But then there are also a lot of interesting things to learn when it comes to constraint optimization. And that's what we are going to do now. So, constraint. There are also some nice questions that I found to make it a bit more hands-on. And then we will cover this from now on till next week. There are 3 lectures to do the constraint. And then we will start with machine learning, where we will apply these directly to machine learning problems. But the subject is called system optimization and machine learning for a reason, because even without the machine learning part, I think knowing optimization is an important skill for a modern engineer. So in that sense, optimization is a goal in itself. Good. So constraint optimization, we'll talk about the formulation. We will come back to the sets and constraints, Lagrange theory, KKT conditions, sensitivity, and some solution methods for constraint optimization. So here are the suggested reading. It's more than you can spend time on, but still you can scan and see which parts apply. And there's some overlap between them. So here's the problem. Okay, the problem is, what is the difference? It's this part. Now, I am looking for a solution inside a constraint set, inside the set, right? In the domain of f of x. So it's not the whole universe. X belongs to some set. So in the continuous optimization formulation, decide on a continuous vector, x r to the n, of dimension n, the same. Maximize or minimize an objective function. Good. These two we had that before. Now we have on a constraint set. So we want to find the solution on the constraint set, right? So the top of the mountain may be there, but maybe there is a boundary. I think that there is an example, right? Maybe it's the top of the Himalayas, but then I'm in one of the countries. And then I don't have visa. I cannot go to the cross of the border. So when I try to climb to the mountain, then I come to the boundary, and I have to stop there. The maximum is for me there, right? I think people are fighting about this, so I shouldn't make comments too much about Himalayas. So or anything else you can think of, right? So there is some reason why you cannot find the real top, because you are constrained. It's as simple as that. Then I have the solution, and f star, and I'm using star again. It's my thing. Some people use f opt in the superscript. That's a bit more cumbersome than putting a star. And then everything should have this set. X belongs to the set. But what is this constraint set, and what are its properties? We'll come to that. We already started in the beginning. I'm a bit ambivalent how I should do it next year. Should I move that set stuff to here to constraint, or should I do it in the beginning and get rid of it once for all? Maybe I'll ask you your opinion later on that. But maybe before then, there is this important question. What happens when X is empty? What if someone gives you conflicting constraints? Then your X is element of this set capital X. But what if this constraint set capital X is empty? Then you have no solution, right? It happens more often than you can think. Sometimes you don't have a solution. So first thing actually in optimization, in constraint optimization, to do is not trying to solve this, decide on which method I use, which direction to go, what are the steps. First thing you need to check whether the problem has a solution or not. Because if this capital X set is empty, then you have no solution. Then the answer is trivial. Maybe I should do that in the final exam. Now that I think about it, that's a nice trick question, right? So I can give an optimization problem with conflicting constraints, and then some will lose a lot of time trying to solve it. There's no solution. Okay, good. I sometimes give away questions like this. So the thing is, of course, when you give a set, it's immediately obvious if it's an empty set or not. The thing is, most of the time, constraints are defined through the functions. So just like we have our objective function, there are inequalities, set of inequalities, and set of equalities, constraints. These two define your constraint set, where X lives. That's your capital X, right? So these are called inequality constraints. These are called equality constraints. In this notation, this is Boyd's notation, by the way. F0 is the objective function. Right? Now, objective function is objective function. You can call it what you want, right? Once you know what's going on, you can immediately understand it. So these equality and inequality constraints define the constraint set X. This is what usually happens with the problems you encounter, because you don't try to define a set as a set, but you are constrained by different things like power constraints, or communication rates need to be at least this much. You cannot pass more than some amount of current through this wire. All those stuff from any field, engineering field, they come to you in these forms, and therefore those make up your constraint set and the domain of the optimization problem. Mathematically, it's easy to say I'm using X. Sometimes people use D, which is the intersection, right? This means intersection of the domain of Fi. So that means that all of these, the domains that each of the inequality that determines the set, each of those sets are intersected with also the equality sets. All of them are intersected because all of the constraints need to be satisfied in your constraint set, right? Not just one or two. So that means intersection. Therefore, when you solve the canonical problem, this is the canonical form. When you go to Boyd's book or Bartsekas's book or any good book, this is the canonical form of how you do some continuous optimization or even discrete optimization. So then the solution will be infimum of the objective, such that this X satisfies all these constraints at the same time. Right, one by one. So that's why when you are given it like this, it's not immediately obvious whether it's an empty set or not. Actually, it's much more subtle. You need to really work it out, find that intersection set to figure out, oh, is it really empty or not, right? So if they are given as intricate functions, you may have a case where you have your domain is empty, then there is no solution. Okay. Any questions? Yep. Inf means min. When you have an open set, inf and sup, supremum and infimum, instead of minimum and max. If you don't know about it, whenever you see inf, use min. Whenever you see sup, max, replace with max. Supremum is max, supremum. Infimum, inf is min. Okay, like if you haven't learned it until now, yeah, don't worry about it. That should have been covered somewhere, right? No? That becomes relevant in open sets. I'm going to work with always closed sets, so min, there is always a min. So min and max. This is a bit more rigorous when it also generalizes to open sets. All right. Good. So we have maybe a couple of more minutes. So we come back to the sets. So now that I have a constraint set, remember the constraint objective functions being convex, right? Objective functions being convex makes our life easier in optimization because it's nicely bowl-shaped or mountain-shaped, and I'm climbing to the unique global maximum or the bottom of the bowl, minimize it, right? So the functions convexity makes my life easier. Just like that, the domain sets, constraint sets convexity also makes my life easier. So actually, convex optimization means, in the constraint case, in unconstrained case, it means the objective function is convex. Then it's a convex optimization problem. But if it's a constrained optimization problem, you not only need the function to be convex, but also the domain, the constraint set to be convex too. If they both need to be convex for the problem to be convex optimization. If the objective function is convex, constraint set is concave, non-convex, then it's not a convex optimization problem. Okay, it's not an easy problem. So both set, constraint set, and the function need to be both convex for it to be qualified as a convex optimization problem. Therefore, convexity of these sets are again important. So you see, this is a convex set. This is not a convex set because when I choose any 2 points, when I find any 2 points here, just one set of points for which when I connect, they fall outside the set, then this is not a convex set. And as you can imagine, finding the minimum, maximum in this shape, intuitively will be more difficult than finding the minimum, maximum in this shape. Yeah, you can imagine, right? So if I'm doing some gradient, you can see this will be nice, smooth going, nicely oval, this convex shape. Here, maybe if the maximum here is and I start here, iterative algorithm needs to turn this corner. That's a bit intuitively more difficult, right? So when you have a non-convex, then the constraint set is non-convex, then it is difficult. So it's not a convex optimization problem anymore. Here, this set is also non-convex because I can choose this point, and this is the open set part. I draw the line passes through the open set, so line goes outside the set, therefore this is not a convex set. And the last concept, and we stop here, then I will go a little bit about the different convex sets and polytopes, and then we'll go to the Lagrangian theory, is the convex hull of a set. So denoted, different ways of denoting it, is one way is here, conv C, is the set of all convex combinations of points in C. So if I have a set C, just like this, for example, then of all the points in C, I can take the convex combinations, right? which is this. This is the convex combination. So theta 1 to theta k, each of them positive, non-negative, and they add up to 1. So half 0.3 plus 0.2 plus 0.4 plus 0.1. So they add up to 1, right? And then they're all positive. What it means is if I'm giving these collection of points, let's say the set C is a collection of points, that's a legitimate set. Is that a convex set? No, because I can choose any 2 points. If I'm just given the points, I mean. If I'm just giving some set of points, right? Is this a convex set? Absolutely not, because I can choose any 2, draw a line. That line doesn't belong to the original set, so that's not a convex set. But I can take these points, and if I do this, then this is the convex hull of those points. Then convex hull is automatically convex, because it covers all that, space. Because you're doing all kinds of combinations between them, so it covers the whole area. Or you can take a non-convex set like this, and when you do the convex hull, it convexifies it. Convex hull of it becomes convex, as you can see here. So therefore, convex hull is important, right? Let's say you are given a non-convex optimization problem with a non-convex constraint set, maybe it makes sense to look at the convex hull and solve the convex optimization problem with that convexified version of it. And then that should give you some type of an initial starting point, at least, to solve that non-convex problem. So that kind of is a good thing to make life a bit simpler. So it is important that you hear this concept, convex sets and convex hull of a set. And that's where we stop today. Then next week, you have the slides already. Enjoy the workshops. And then the week after, hopefully, we'll start machine learning.